A heat exchanger was installed purposely to cool 0.5 kilograms of gas per second. It sounds like our MG. Its molecular weight is 32, and K, or the Boltzmann constant, is 1.32. The gas is cooled from 150C to 80C. So let's call that TG1, 50 degrees C. Let's convert that into Kelvin first. It is 423 Kelvin. And TG2 is 80 degrees C, which we also need to convert into Kelvin first. 353 Kelvin. Water is available at the rate of 0.3 kilograms per second. Well, let's call that MW at 0.3 kilograms per second. And at a temperature of 15 degrees C. That sounds like our entry temperature. 15 degrees C. Also converted into Kelvin. Calculate the exit temperature of the water in degrees C. So we are trying to find TW2, which is our water's exit temperature in degrees C. So we'll need to convert this later. Okay, so let's try drawing this problem. Here we have our heat exchanger. This is where the water is flowing through. So this MW is right here. Entry temperature of the water, exit temperature of the water. And then we have the chamber where the gas is going through. So let's call this gas, and this is where Mg is. This is where Tg1 is, and this is where Tg2 is. So now we can see that this is a conservation of energy problem. So energy in equals energy out. Okay, so let's continue from up here. So first we need to take into account the gas that's entering the heat exchanger. CPG is the specific heat of the gas, and it's entering at the temperature of Tg1, and there is also water coming in, so MW, specific heat of water at constant pressure, and this is TW1. Let's move this here. Now it's the same for what's going out. So this one is now Tg2 because it's leaving the heat exchanger. And we do the same for our water, TW2. Okay, so far we know Mg, we don't know CPG, we know Tg1, we know MW, we know specific heat of water, we know our entry temperature for the water, again we know these, we know the exit temperature of the gas, we know the mass flow rate of water, we know this, and we are trying to look for TW2. So we can't solve this yet because we still don't know what this value is. The specific heat of the specific heat of the gas, rather. There is one way to get this. So in order to find our CPG, we will need to use the molecular weight and the Boltzmann constant. So the formula for that is CPG is equal to Kr over K minus 1. Now keep in mind this is the individual gas constant, so we can't use the universal gas constant. We already know our K, but we still need to find the individual gas constant. Now that can easily be found by using this formula, which is simply the universal gas constant divided by the molecular weight of our gas over K minus 1. So now we can solve everything. You just need to remember the value of the universal gas constant. And that would be 8.314. Molecular weight is over here, it's 32. Divided by K minus 1. Let's see what we get here. And we get a specific heat of 1.0717 kilojoules per kilogram Kelvin. So now we have this. So we can do a shift solve for our water exit temperature. Let's write those down real quick. Actually, there is a better way of writing this relationship. Let's start with the gas. CPG TG1 minus TG2. And then we have our water W CP TW2 minus TW1. Okay, so all we did here was transpose. Now we can return, or rather now we can write down the values. And we get a value of 317.86 317.86 Kelvin. And all we have to do now is convert this back into degrees C. And we get a value of 44.86 Kelvin. And that is our final answer. I hope this helped. Consider liking, subscribing, and supporting me on Patreon. Thanks, and good luck out there.